All right, now let's start going through some of the actual fMRI data quality using the quality check. So we're going to go through pretty systematically through all the sections of the QC HTML for this bootcamp subject here, the AFNI Data 7, more recent bootcamp subject. And you can follow along with any subject using a modern output here. If I type ls-ltr, I see I have the QC directory. So I'm going to run open apqc.py -in files, QC tab, in tab to type quickly. And we can ignore that red error, as we said before. Okay, and so here's the HTML. We had started in the overview section about adding in ratings and comments. So if we click, we can add a rating. And if we control click, we can add text, or we can open this up to view the text. That's okay. What I'll do now is I'm just going to click clear here, or double click it, and that removes everything here. So you can't undo this, so I'm just going to do it now so we start with a clean slate. Okay, we've talked a little bit about some of the buttons and features here. If you hover over, you should have a hover help that tells you a little bit about what's there. The rating system and the rating buttons here. And then also there's the help button here if you want more description or links to other things as well. All right, so the top section here, the vorig, is for volumetric views of the original data. This image here, as described here, so this is looking at the raw EPI data. It's a single volume viewed as a montage here. And what we're probably going to look for are features like the field of view. So for example, there's a little bit of a problem even here that the field of view for this data isn't quite clean for the top of the data. There's going to be a little distortion there. Certainly at some point, the bottom of the field of view will cut off something in the human head, either the neck or the cerebellum or something like that, brainstem. And in this case, you have to know whether you want the brainstem there or not. You can also get a sense of tissue contrast, a little bit of some EPI distortions, things like that. Can you see features? And so overall, to me, this data looks pretty reasonable. With EPI data, we know there's going to be some dropout and distortion, and we'll see how we get maybe some better views of that. The dataset range is also displayed here. Sometimes this value, if it hits 4095, probably is the maximum that would get in many of the scanner outputs. If you hit that, you might be saturating, and there'll be some warnings about some of these things as well. Having obliquity is certainly fine. This data set does not, but we just put it here for information's sake. And there we go. And we saw earlier, if I wanted to look in between more interactively, I can click NV to open up a NiiVue browser and surf the data for cutoff or distortion or whatnot. And if I wanted to do this in the AFNI GUI, I certainly could as well. And the nice thing is with any of these buttons that I don't even have to select the volume. What I want is there already, and once it's loaded, I can surf through it however I want. The next set of images here, these are a very recent addition, and this is something we'll come back to even within this HTML, and we're also working on a longer description of this, but basically there are some important features that we can see by looking at the variance of the EPI data set here. So this is the variance across run 1 of this data set. The data in this case have 3 runs of task-based fMRI with a block design and audiovisual task. This is looking at the variance of just the first run, and we're going to see that actually this bright vertical striping here is a problem, and we'll come back to that. In general, you will see the edge of the brain pretty bright because there's always some amount of subject motion. And so there adds to be kind of a lot of variance around there. It's not unusual to see higher variance in the middle of the brain as well, like here. But these vertical features are something that we'll come back to. The anatomical data set here, it's also important to check. It plays an important role in a couple ways in the fMRI processing. So this is the anatomical that has been skull stripped. I can just tell that from the name. This was skull stripped by SS Warper probably, or SS Warper 2. And again, in this case, what are things I'm looking for? Probably having the whole field of view, so no part of the brain is cut off. This certainly doesn't appear to be. The skull stripping itself looks pretty good. I can see maybe little things around, but overall it's quite good and recognizable. And the tissue contrast, that the ventricles are dark and the gray matter is kind of like intermediate brightness and white matter is white. There isn't a large amount of brightness in homogeneity, which maybe could affect alignment or something like that. So these are all the things that I would notice looking at this, and kind of checks a lot of boxes for being fine. And excuse me, this final panel in this vorig section, before we get to this line here, shows the initial overlap of the EPI and the anatomical data sets. This is where the alignment process for these two, which plays an important role in our study and processing, is shown. If either of the data sets or both of them have obliquity, there'll actually be two images here. It's the second one, always the lower one, that matters the most for where, when obliquity is taken into account, where the overlap of the data sets are. So in general, if your DICOMs have been converted well and the coordinates were kind of sensical and the data came from the same session, we would expect pretty good overlap between the EPI and the anatomical. Sometimes with conversion processes, or if a subject gets out and goes back into the scanner, which is maybe technically still the same session, there might be poor overlap, large rotation, large shift between the two data sets. That may not be a problem, but it's just something we want to be aware of. So in general, we would prefer to have this show good overlap, such as here. It doesn't have to be this good, but if there does get to be a problem with the EPI anatomical alignment, which we'll see next, then that would be something we would troubleshoot here. So this is kind of here for maybe later reference, because this always comes up if there is that question. So at this point, we could decide how do we feel about all the things here. At the moment, we might feel pretty good, or maybe a little bit of a question mark we'll come back to with this one, but for now we might say that this is pretty reasonable. All right, and then we could either scroll down to the next section, or we could click on the E to A, so the EPI to anatomical alignment. When we're judging this, as we see here, the underlay is the EPI data set, and the overlay is the edges of the anatomical. And so what we're looking for is all these interior features matching up or not. And this is where it really helps to have good tissue contrast for both the anatomical and the EPI. For the anatomical, so the edges are clear, and for the EPI, so we can see where they are. And they're, funnily enough, the outer edge of the brain actually might be one of the more poorly aligned parts. Certainly when we're down in the more inferior slices and near the edge of the field of view, we might see some dropout and things kind of come and go here. There can be bright CSF that we see here popping up a little bit, or the skull stripping might not be perfect. The EPI is also a little distorted, but in general, if we look at where the sulcal and gyral features are, the ventricle boundaries and things like that, I would say the alignment is quite good for this subject. Something that we'll see in a few different ways, but I like looking for in this particular image, is getting a sense of the EPI distortion. So the idea is the anatomical edges should be minimally or have almost no geometric distortion or dropout. At most, maybe skull stripping issues, but here we can see the boundaries of really what we would consider the anatomical brain. And the EPI, when we look here in these sagittal views, we do get a sense of where there's dropout. Obviously, the lower parts of the brain that we see with the anatomical, there is no EPI data because the field of view was different between the two different acquisitions. And but here, there really probably should be data here. So if you see down to this set of slices, when we see here and it's dark in between the edges of the anatomical, this is because there's dropout caused by the sinuses. And this is a very, very common and also very deeply problematic issue with EPI. It is very difficult to get signal here in these regions. So the VMPFC, inferior frontal, and also into the subcortical parts of the brain here. So if you care about this in your study, you really need to focus and make sure, do you have adequate signal there? In this case, this data set really doesn't, and we can see this nicely and clearly here. So this is something I would look at. Again, if my study depended on these regions, I'm in trouble, but this data itself looks pretty standardly reasonable. The geometric distortion, there's a little bit I can see, but it's not what I would consider hugely problematic for most EPI data, so I'm willing to say that that's pretty reasonable. One thing I'll also note, maybe I should note here, is if I wanted to check this out now with like the NiiVue functionality, because we're looking at an overlay and underlay feature here, actually we can toggle on and off and see it's not the edges of the anatomical at present, but the actual anatomical. It's a little bit tricky because the tissue contrast between the anatomical data set and the EPI is opposite, right? The ventricles are bright for the EPI and dark for the anatomical. So if I turn that off for a second, if I turn on the AFNI view for this data set, this also actually will not load up the edge data set of it, because that's not a permanent data set in the AFNI proc output directory. But I do have the overlay here, as this pop-up tells me. The overlay is the anatomical and the underlay is the EPI. But in this case, the overlay anatomical, the color bar that it's been given, is such that the ventricles are bright for standard T1 weighted, the white matter is dark. And if I hit the O key, as this pop-up message mentions, to toggle on and off the overlay, I can get a good sense of the relative difference and distortion between the anatomical, which I'm looking at now, and the EPI. So they're not perfectly matched, they are different data sets, but the same tissues, the gray matter, CSF, and white matter, the relative brightnesses should be the same between them. Okay, so this gives a sense of overlap, quality of alignment, sulcal gyro features, and also a little bit of distortion that you can see in different parts of the brain. All right, so that's the AFNI view for this alignment. And as we keep on scrolling, or just click on va2t, this is another alignment that we're looking at. So this is the anatomical to the template data set for this bootcamp example. And again, I have an underlay and an overlay that's edges. Here the underlay is the anatomical, and the overlay is the template data set, or the edges of it. Now in this case, when I look at the boundaries and sulcal and gyral features, again, that are key for really judging alignment, I can tell that these are aligned, but I might be a little bit disappointed in kind of the quality of alignment for these. The sulcal and gyral features don't really match up so well. Now there are a couple reasons for this. One, relative to this image here, the underlay and the overlay come from the same subject's brain. So one has a little distortion, the EPI can be a little geometrically distorted and things like that, but ultimately it's the same person, underlay, overlay, same subject or participant. In this case here, this is one participant's anatomical aligned to the template, the MNI, and so actually they do have different sulcal and gyral patterns, shapes and things like that. So I might expect there to be some difference. If we did real processing and we had full nonlinear alignment for our processing, then what we might expect is that this alignment would be better quality. In this case, actually, I would say it is not great quality, but that is simply, in this case, one reason is due to there being a different subject than the template brain. The other one is that we only used affine registration for this quick bootcamp example. And something I can do kind of quickly just to make this point, I'm going to open up another terminal, and I'm going to actually open up the APQC. If I go up, I had processing here from nonlinear processing, nonlinear alignment to the template. just so we can see maybe what I might expect in that other case. Now, we'll talk about in a later video about how I can open up multiple QC HTMLs simultaneously and have them locked together and jump together. In this case, I'm just doing a kind of quick cheating way, so they're not really interactively locked together. But I've opened up a QC HTML from nonlinear alignment and processing, which you see here. And now if I click on this other tab, this is my affine case. So let me just go back and forth between these as I click left and right. I can actually also use Control Tab, and that's a preferable way. So this is the affine alignment and this is nonlinear, just to say this is what I'm going to be much more expectant to see with full nonlinear alignment in a more real processing example. In the bootcamp case, we just did affine for the quicker processing time during the class. So just to get a sense of the level of detail and alignment, this is what I would expect with nonlinear. See, especially up here in the upper cortical features, and then here it really looks more of a jumble mess. Interestingly, for human brains at least, these upper cortical features, the more superior slices, this will show much more individuality, and so here I will probably see poorer alignment than down in the subcortical parts where the human brain tends to be more similar. So what I would expect to see more similarity between the two alignments down here, or it's less obviously that affine isn't so good versus in the superior regions. So, all right, that is looking at our alignment here, and that's again a necessary and useful thing to look at visually. The cost function does what it can do quantitatively, but to really judge did the cost function do a good job, it really takes a visual inspection. And finally, the last bit of this va2t section, the anatomical to template, is we'll see the mask that was estimated. And so we're not going to multiply this by our EPI data because we want to see things everywhere. But looking at this mask data set, and we're back again in our starting affine example from the bootcamp, this shows us where we have pretty strong signals. So this is where auto masking of the EPI intersected with the anatomical masking produces the kind of overall mask for this subject, where we would have what we would consider reasonable data. If you notice, it doesn't include absolutely everything. And this here in these regions gives us a sense of that dropout. If you can see, these inferior slices do have some data, but in this case, there's missing data certainly here. That's because it had very low signal. We'll also see a signal to noise data set later, and maybe due to alignment or even some dropout or distortion, there's a little bit also that we don't see the mask covering out here at the edge. Later, when we would go to group analysis, we might intersect this mask across subjects, or might consider missing data, anything outside of here for this subject. But this mask also gives us a good sense of alignment. So if EPI and anatomical data sets didn't align well, or the anatomical to the template, this mask might look a little odd, or missing regions. And also just the EPI data itself and where there's coverage, this will show it. And something that can also be nice is if you open up the NiiVue in particular here, you can see this volumetric rendering. And sometimes I like to open this up and then click C, the clipping button, and now you can surf through it and see it, the masking in this volumetric way, which I just find helpful. It's a nice visualization, as well as any of these. And similarly, I could open this up in the AFNI GUI. All right, so overall, I would say this alignment isn't great. So this might be something, if I was in a real processing case, I might put a question mark here and say, did we do nonlinear alignment? And leave that as a question for later to check with someone else in the lab, or to discuss with someone else in the lab, or something like that. All right, I'm going to pause here for these first few sections, and then we'll continue looking at more of the HTML in a different video.